Hello everyone, my name is Dr. Dandekar. I graduated with a PhD in machine learning from the Massachusetts Institute of Technology in 2022. And now we are on a mission to make artificial intelligence accessible to all. I am making this video as the introduction video or the first video in the new series of lectures which we are launching, and that's in the field of hands on large language models. We have covered a huge number of lectures in this series called Building Large Language Models from Scratch. There are around 35 to 40 lectures in that series, in which we introduce the nuts and bolts of building a large language model, building your own chat GPT completely from scratch. While that is incredibly useful and a very, very important building block and a important fundamental step in your knowledge as a machine learning engineer, what is equally important is to understand how to use large language models in practice, how to apply large language models in real life scenarios, and how to build and deploy applications using large language models in industries. The whole aim of this lecture series, which we are starting, is to show you how large language models are actually used in practice and to develop a huge number of applications with LLMs. We will follow the approach which is the trademark, I would say, of our teaching style, and that is in depth content with a lot of attention to detail. So the content will be very much detailed, and at the end of this series, you will get a fundamental understanding regarding building large language models, deploying large language models in production. And along with the theory of LLMs, which we have covered in another lecture series called Build LLMs from Scratch, this lecture series will teach you the applications, and hence, with both of these skills, you will be a very strong machine learning and a large language model engineer. Similar to all the playlists which we create, this playlist will also be very comprehensive. It will probably include more than 25-30 lectures and will cover a wide range of applications in large language models. So let's get started with our first lecture of this series. Hello everyone and welcome to the first lecture in the hands-on large language models series. Before we get started with the lecture itself, I want to show you the reference book which I'll be following throughout this lecture. So last month, an amazing book on this topic came out on O'Reilly, and it's written by the authors Jay Alamar and Martin Grutendorst. These are amazing researchers and engineers in the field of large language models, and I've been actively following Jay on LinkedIn for a very long time now. The content written by Jay is one of the most detailed and very illustrative content which I've come across. So when I saw that this book is getting launched, I was incredibly excited and it did not disappoint me. So if you look at the table of contents in this book, this is exactly what we'll be covering in this lecture series. So the book itself is divided into three parts. In the first part, we will understand large language models, intro to LLMs, tokens and embeddings, and looking inside large language models. In the second part, we'll look at pre-training large language models and how to use the pre-trained large language models. So here is where the application really comes into the picture. We'll see several applications such as text classification, text clustering, topic modeling, prompt engineering, advanced text generation techniques and tools, semantic search, retrieval augmented generation, and even multimodal large language models. Multimodality is extremely important because large language models don't just deal with text, they deal with several other modalities such as sound and videos as well. So part 2 covers the bulk of this book, and these are all the applications which will be understanding in this lecture series. However, the book does not stop here. There is also part 3. Let me go back. Yeah, there is a part 3 over here in which there are three things which are covered: creating text embedding models, fine tuning representation models, and fine tuning generation models. There is a difference between representation models and generation models, as we'll be covering subsequently in these lectures. But for now, just know that we'll be exploring fine tuning in the third part of the model, in the third part of this lecture series. And in the second part of this lecture series, we'll see how to use pre-trained models for performing several applications. Fine tuning is another training stage which is built on top of pre-training. That's equally important, but we should know when to use a pre-trained model and when to use a fine-tuned model. With this background in mind and with this structure which we'll be following in this lecture series, let's get started with today's lecture. In today's lectures, I just want to cover a bit about the background and the history of large language models, not just looking at ChatGPT, but the whole history of large language models and natural language processing itself. The reason I'm covering this in the first lecture is because you need to appreciate the age in which we are living in right now. Discoveries in the field of natural language processing have been happening for more than a century now. And it's only at this moment when the critical breakthrough happened with ChatGPT. But we should not forget the contributions of the researchers who have worked so hard in the previous century to bring us to this stage. Why am I calling it the ChatGPT revolution? Well, when ChatGPT was launched, it had 1 million active users in just 5 days and it had 100 million active users in 2 months. Facebook took years to reach this scale, but with ChatGPT, it just happened in a month of days. It just happened in few months. 100 million active users in just 2 months. Can you imagine? The reason there were so many users is that the value which ChatGPT provided was very high and it was incredibly useful to students, to researchers, to engineers. In fact, without ChatGPT, we would not have been having this lecture in the first place. ChatGPT just completely changed everything around us. So, before learning about large language models, we need to understand that there is a new terminology which is language AI. So if you consider AI as the broad field, if AI is the broad field, within AI there is a subfield which I am marking with the purple color right now, and that is the field of language AI. This is the subfield of AI that focuses on developing technologies which are capable of understanding, processing, and generating human language. ChatGPT comes under the domain of language AI. And you may have heard about the term natural language processing before. In fact, language AI or NLP are terms which are used interchangeably. Language AI or NLP. So, one thing which I would like to clarify here is that although ChatGPT has revolutionized things, the term natural language processing or the field of natural language processing has been around for a very long time now. And this invention can be thought to be as a part of this field of NLP. However, many of us don't know the term language AI, and so it is just introduced over here. And language AI can be interchangeably used with the term natural language processing. Okay, now let us start understanding a bit about the history of language AI, the history of natural language processing, and how did we get to the stage which we are in right now. So here is a figure which is taken from the book, and I would say that the time at which real changes started to happen in this field was around 1980 to 2000 when this bag of words approach was introduced. So the whole game of natural language processing is about taking language, taking words, taking sentences, converting them into vectors and learning something from these mathematical representations. So it really boils down to how can you take sentences and how can you convert them into mathematical representations. The bag of words approach really did that for the first time. So here I am just opening the Wikipedia article for the bag of words model. An early reference to bag of words can be found in 1954 article on distributional structure. So this has been around for quite some time. So I would attribute it somewhere from 1960s to 2000s, since when people have been introducing and using bag of words. So what exactly is bag of words? Let's take an example. So let's say we have two text documents. The first text document reads like this: John likes to watch movies, Mary likes movies too. Let's say that's the first text document. The second text document is Mary also likes to watch football games. Now, what's done in the bag of words approach is that a list is constructed, or rather, you can think of it as a bag. A bag is constructed for each document, where you list down all the words which are appearing. So here you can see in the first document you list down John likes to watch movies, Mary likes movies too. And in the second, Mary also likes to watch football games, right? Now, based on each document and the words which have been written, a dictionary is created next. So for the first document, here is the dictionary. John comes once, likes comes two times, because likes comes here, and so likes comes here and likes comes here also. Then two, the word two comes once, watch comes once, movies comes twice, Mary comes once, and TOO comes once. Similarly, the second dictionary is created for the second document, and that's bag of words too. So you can see that in the dictionary, which is the ultimate bag of words, there are unique words and their frequency has been mentioned. So for each document now you have a vectorized representation. What are these vectors? The vectors are just the frequency with which the different words appear. This is the simplest way you can convert a textual document into mathematical representations through vectors. And bag of words is the foundational technique through which many other techniques in natural language processing actually emerge from. So we need to be mindful of this advancement in NLP. Then the second major breakthrough I would say came in 2013. In 2013, the word to wake approach was introduced. Now, what's word to wake and why is it different than bag of words? Well, the major difference is that bag of words does not take into account the meaning of words at all. For example, if you consider cat and if you consider kitten, the advantage of dealing with words is that these two words are related to each other, right? They have meanings which are similar to each other. And that similarity of meaning, that semantic understanding behind words and what words represent, that's completely missing in the bag of words approach. And this was really the first time this problem was tackled was, I would say, with the word to wake approach which was introduced in 2013. So if you go to this paper called Word to Wake, this Wikipedia article rather, you will see that this was a technique which was developed by Google and published in 2013. What happens in this technique is that you take a document, you convert it into words, let's say, and then you convert every word into a vector in a higher dimensional space. The reason we convert words into vectors is that if two vectors are similar to each other, which means that their angles are aligned with each other, it means that they are similar to each other. So, for example, cat and kitten will have similar meaning, right? So, these vectors will be similar to each other. Whereas, let's say, cat and something completely different, meteor, they don't have too much meaning. So, then there will be vectors which are at 90 degrees. So, in a sense, the distance and the angle between vectors can capture the semantic relationship between words. So, word to vec represents word as a higher dimensional vector of numbers and which captures the relationship between words. So words which are closer together with each other, they are represented with vectors which are nearby each other, and the distance is measured by this metric which is called as cosine similarity. So, for example, the vectors for walk and ran will be close to each other. The vectors for Berlin and Germany will be close to each other. A simple demonstration of how this works is shown in this interactive web page. So what I've done is that I generated some text using Chat GPT about Harry Potter, and the reason I generated it is I want to show you how this word to vec is created. So essentially, you have a text like this, right? What you then do is that you list down all the tokens, which are the individual words, and the frequency with which they appear. So this is what you see here, the tokens. In the heart of wizarding world, Harry Potter stood tall, his black messy hair, lightning shaped scarred, etc., etc., and the frequency. Then what you do is that you take the tokens and then you write down the tokens which are near to the current token. So for example, in and out, in and though are close to each other, because if you see, the starting is in the heart of the wizarding world. Then in and heart are also close to each other, in and off are also close to each other. Now if you see wizarding, heart and wizarding are close to each other. So essentially you collect the pair of neighbors and these will serve as the training examples. So you may think, okay, what's training here? Do we have some kind of a model? Yes, there's a neural network essentially. So you see these training examples here. We need to train a neural network to take in the inputs and understand which words are near to the current word. So for example, I've just demonstrated this neural network over here. So yeah, this is that neural network. So words are converted into input and target pairs, and then a neural network is trained. So for example, here is an input and a target pair. So input is heart and the output is off, because off is closer to the to heart, right? So this is the input and output, and we want to train a neural network so that when heart is the input, the words close to heart are the output. So neural network is trained to predict if two words are neighbors or not. So for example, cat and kitten will be neighbors, right? Because they would usually mean the same thing, and they would appear in sentences near to each other. So a neural network is trained, and let me actually show how the training proceeds. So if I click on train model, here is where the neural network is getting trained, and let's see the visualization. So here I'm running 5000 iterations. Do you see on the screen right now, the different words are represented as vectors, and the whole goal is that words which are near to each other will be closer together in this vectorized space. So for example, heart and off, they came together, right, in the sentence, and here you see in the vectorized space they are closer to each other. Now, in the actual word to construct the actual vector embeddings, it's done in a much higher dimensional space, and it's trained on a huge amount of data set. So, considering millions of data sets, cat and kitten will be closer to each other. Here, I am just looking at one data set. So, but this explains intuitively how the word to vec works and why it is a fundamental advancement compared to bag of words. Bag of words could not capture semantic meaning. So, words to vec is another way of representing text, another way of representing sentences, words in a mathematical representation in terms of vectors. But now the vectors capture the meaning. Okay, so after we finished word 2x, the third major development happened with respect to the attention mechanism. The first paper on attention came out in 2014, and this was called as the Badhanov attention mechanism. The main idea behind attention was that when you're looking at vector embeddings, right? Let's say you're looking at vector embeddings for each of these individual words. You are capturing the meaning of one word. Let's say cat and kitten are closer to each other, but you are not capturing, let's say if you are looking at this sentence and if you are looking at grounds, which other tokens or words in this sentence are more similar to the word grounds. That is called as attention. So attention is actually capturing long term dependencies in the sequence, and that is very helpful when predicting the next token or the next word given input sentence, just like how chat gpt does. I think here I also have a simple representation of the attention mechanism. Yeah. So attention allows a model to focus on parts of the input sequence that are actually relevant to each other, and that helps in generating the next token. I'm not going into too much details of the attention mechanism here because I plan to cover that also in the subsequent lectures. But I just want to show you that attention was introduced in 2014, and then it was introduced in another paper in 2017. The reason this paper caught all the attention and why it is much more famous than the 2014 paper is that this 2017 paper titled Attention is All You Need introduced the transformer architecture. So let me scroll down a bit and show you the transformer architecture. In the Build Large Language Models from Scratch lecture series which we had 7 to 8 lectures to explain this whole transformer module. The reason this paper got so popular is because the transformer architecture is the main architecture which powers GPT models, and in fact all the further advancements which happened in natural language processing. And although the attention mechanism which they use was derived from the 2014 paper, the transformer model or the transformer architecture which they introduced completely changed things. So when I have written here 2017 and attention, Actually, what I should be writing is that attention was actually introduced in 2014, but what is more important is the transformer architecture. The reason it transformed natural language processing is that multiple transformer blocks could be stacked together, and that just made it very easy to build very large models. Earlier, it was quite difficult to build large models, but transformers can be stacked on top of each other. And it turned out that the more transformers you add, the better the model gets at predicting the next token, and that is because of the attention mechanism. So if if the transformer architecture is the car, the attention mechanism is the engine which drives the car. Okay. Now, along with attention mechanism, there was also a BERT model which was introduced in 2018, I think. So let me go to this paper. Yeah, this is the paper BERT, pre-training of deep bidirectional transformers for language understanding. So based on the transformers paper, there was a model called BERT which was introduced, and BERT remains a hugely fundamental advancement in natural language processing. And till now, BERT is used in a wide range of natural language processing tasks. Everyone remember GPT because of Chat GPT. That's the product. BERT does not have any product associated with it like Chat GPT. But you should not forget that this model is still widely used in a huge number of industrial settings because it's an awesome model and it captures several aspects of language understanding. It's based on the transformer architecture. So this is the paper which came out, and this paper came out before uh, the next advancement, which was GPT. So the BERT paper came out before the GPT paper. GPT is generative pre-trained transformer based on which Chat GPT is based. So here is the generative pre-trained transformer Wikipedia article, and the paper related to this came out just after the BERT paper came out. The architecture between BERT and GPT differs from each other with respect to their encoders and decoders, but both of them are fundamentally based on transformers and the transformer architecture, and both of them represent huge significant advancements in natural language processing. Now, based on GPT, there were huge advancements which happened later. So after GPT-1, there came GPT-2, then came GPT-3. Now we have GPT-4. Chat GPT came out, which is the product version of GPT 3.5. Similarly, researchers also developed a lot on the BERT architecture. Then Distill BERT was introduced, Roberta was introduced. So here is a paper on Roberta, a robustly optimized BERT pre-training approach, and this also has a huge number of citations now. It's an advancement or a modification to the BERT approach. All of what you're seeing on the screen right now comes under the field of natural language processing. Due to this Chat GPT, we all think that everything is related to Chat GPT, right? But it's not. BERT architectures are equally popular and they are equally useful. Then what you see in green, they are T5 switch and Flan T5. There are other type of NLP models which have become famous. So for example, the T5 model is a text-to-text transformer model. It's introduced by Google AI in 2019. They have also been used in a wide range of applications such as chatbots, machine translation systems, text summarization tools, etc. So when you think of natural language processing, don't just think of GPT. Think about Word, think about T5, think about Roberta, and your view of NLP should be so broad that it encompasses all of these different types of models. So Flan T5 is another variation of T5. So here, if you can see, I'll just rub all of the things in the color, and I want you to see this history of natural language processing or history of language AI again. All of this, what you're seeing on the screen, has led to the invention of, ultimately led to GPT, Chat GPT, and the advancements in NLP which we are seeing right now. The work in this field has been happening since a huge amount of time, and we need to be respectful and aware of that. So the main purpose of natural language processing or language AI is to essentially take text input and convert it into mathematical representations, which does either of the following things. You can develop a generative model out of it which predicts the next token given the text, or it generates an image based on the text, or we can convert the text into token embeddings, or we can use the text and do a classification problem like converting and or classifying an email into spam versus no spam, etc. So these are the tasks performed by language AI. This brings us to the end of the first lecture, where we covered about the history of attention mechanisms, history of natural language processing, history of GPT, history of BERT, etc. In subsequent lectures, we'll be diving deeper into individual topics, such as we'll be looking at the difference between representative models and generative models, difference between BERT and GPT, etc. These are the introductory set of lectures, and after which we'll dive right into applications. This playlist is meant to be very application oriented, but I do want to cover a part of the introduction initially so that all of us are on the same page. I will also spend some lectures of covering the attention mechanism concept, the transformers architecture concept, and any other foundational concepts which I think are relevant for you to understand the applications part. We should not directly jump to applications, but have a decent understanding of the fundamentals as well. Thank you so much, everyone. I hope you will enjoy this lecture series. I'll look forward to seeing you in the next lecture.